A single teaspoon of neutron star material would outweigh every person on Earth. This is not a fantasy, but the genuine nature of the universe's most extreme laboratory, a neutron star. To understand the fundamental forces that shape reality, we must look to these stellar corpses, where conditions exist that we could never recreate. By the end of this journey, you will have a complete picture of the bizarre, layered reality inside one of these cosmic anomalies, from its crystalline crust to a core that might be made of pure, free-floating quarks. We will venture into a place where matter forms shapes called nuclear pasta and flows in perfect, frictionless rivers. How can a star smaller than a city contain such impossible physics? And what does its heart ultimately look like? What does it feel like to confront a natural phenomenon that defies every rule you know? Gravity always wins in the end. For a star that has lived by fusing elements in its core, this final victory is both spectacular and terrifying. When such a massive star, perhaps 8 times heavier than our Sun, finally burns through the last of its nuclear fuel, the delicate balance that sustained it for millions of years shatters. The outward push from fusion stops, and nothing remains to hold back the star's own immense weight. In less than a second, the core implodes. Think of the entire mass of a giant star, a sphere millions of kilometers across, suddenly rushing inward at a quarter the speed of light. This collapse is so violent, so unimaginably powerful, that it forges conditions we cannot replicate anywhere in our solar system. The core is squeezed with such force that electrons are literally crushed into protons, their opposite charges merging to form a sea of neutrons. This neutron-rich material becomes so dense that a single sugar cube of it would weigh as much as a mountain. Then, in a final act of cosmic defiance, this ultra-compressed core rebounds. It hits a wall of unimaginable density and springs back, sending a shock wave racing outward. This wave tears through the still-falling outer layers of the star and blasts them into the void in a brilliant supernova explosion, visible across galaxies. What remains is the core itself, now a naked, spinning sphere of the most exotic matter in existence. This is the neutron star. Its birth is a story of catastrophic collapse and impossible rebirth. But not every dying star earns this fate. There is a precise cosmic ledger. If the collapsing core weighs less than about 2.2 times the mass of our Sun, it settles into this stable, neutron-rich state. If it is heavier, not even the neutrons can withstand the pull, and the collapse continues forever, birthing a black hole. So every neutron star is a survivor, a remnant that narrowly avoided the ultimate oblivion. Its very existence is a testament to a perfect, violent balance at the edge of what is possible. That surviving core is now a city of pure neutrons. To grasp what that truly means, we need to confront a scale of density that rewrites the rules of reality. A typical neutron star packs about 1.4 times the entire mass of our Sun into a sphere only about 20 kilometers across. That is the distance of a short morning commute, yet it contains a star. This creates a density so absurd it becomes almost a philosophical concept. If you could somehow take a single sugar cube of this material and bring it to Earth, it would not just be heavy. It would weigh roughly 1 billion tons, the combined mass of every human being alive, squeezed into a space you could hold between your fingers. To make it even more tangible, imagine taking the entire mass of Mount Everest, every rock and cliff face, and compressing it down until it could fit inside a coffee mug. That mug would then hold the density of a neutron star's outer layers. How does matter even get this dense? It is a story of ultimate surrender. Inside a normal atom, there is mostly empty space. If an atom's nucleus were a marble in the middle of a football stadium, the electrons would be buzzing around in the very top rows. In a dying star's core, gravity wins so completely that it eliminates this emptiness. It first crushes atoms until the electrons themselves form a degenerate pressure, a quantum mechanical standoff trying to halt the collapse, but past a certain point, even that fails. The force becomes so overwhelming that it drives the electrons right into the protons at the heart of atoms. Their opposite charges cancel out and they merge. What is left is a particle with no charge at all, a neutron. This process, called neutronization, floods the core with a sea of identical particles. This is why we call it a neutron star. Its gravity, now 100 billion times stronger than what we feel on Earth, means that if you could magically appear on its surface, you would not just fall. You would be pulled into a thin film of atoms faster than your nerves could even register the sensation. This unimaginable density is not the end of the story, however. It is merely the doorway. It creates an environment so extreme that the neutrons themselves are forced to behave in ways that seem like pure fantasy. This neutron sea is not a uniform soup. It has layers, a geology as complex as any planet's, beginning with a crust of unimaginable strength. The outermost skin of a neutron star is a deceptive place. It is made primarily of iron, an element familiar to us, but forged here into a state that defies earthly physics. Under the crushing weight of the star's own gravity, the atomic nuclei are squeezed into a perfect, rigid lattice, like a crystalline mountain of iron. But these are not normal iron atoms. During the star's catastrophic collapse, many of them were forced to absorb electrons, becoming neutron-rich and incredibly dense. All the empty space that defines matter in our world is gone here. In its place, a sea of free-flowing electrons moves effortlessly through this metallic crystal. This crust is perhaps the strongest material in the universe. It can be miles thick, and it forms the solid surface of this cosmic anomaly. But even this incredible structure is not invincible. The neutron star spins often hundreds of times per second, and its immense magnetic field, trillions of times stronger than Earth's, exerts titanic forces. This stress can cause the crust to crack. When it does, the entire star rings like a bell. These starquakes release more energy in a millisecond than our Sun emits in 150,000 years, energy we detect from across the galaxy as intense, fleeting flashes of gamma rays. This crust, for all its alien properties, is just the beginning. It is the thin, solid shell over a much stranger interior, a boundary between a world we can almost comprehend and one where physics itself begins to break down. But the solid crust is only a thin shell, a deceptive skin over a far stranger reality. As we journey deeper, the pressure becomes so immense that it achieves the impossible. It dissolves the very concept of an atomic nucleus. The iron lattice of the crust simply cannot hold. The nuclei themselves are squeezed until they merge, their identities lost in a vast, overwhelming sea. This is the outer core of the neutron star, and it is not made of water or molten rock, but of pure neutrons, billions upon billions of them, packed shoulder to shoulder with no empty space between them. This neutron ocean is the dominant feature of the star, making up the bulk of its incredible mass. Yet even calling it a fluid feels inadequate, because here, at these extremes, quantum mechanics takes over from classical physics. These neutrons do not behave like a normal liquid. They become what physicists call a superfluid. A superfluid has a property that sounds like magic. It has zero viscosity. That means it has no internal friction at all. If you could stir a cup of this neutron superfluid, the whirlpool you created would spin forever, never slowing down, never losing a single bit of energy to heat or resistance. It is a perfect, frictionless flow. This is not just a theoretical curiosity. It has a direct, observable consequence that astronomers have actually measured. Neutron stars spin with incredible regularity. their pulses acting like cosmic lighthouses with precise timing. But sometimes, very suddenly, a star's spin will speed up in a tiny, abrupt jump. Scientists call these events glitches. The leading explanation involves this inner sea of superfluid neutrons. Think of the star's solid crust spinning like a rigid container. Inside it, the superfluid neutron ocean is also spinning. But because it is a frictionless superfluid, it can spin at a slightly different rate than the crust. Every so often, as the crust slows very gradually from emitting radiation, the lag between the two becomes too great. The superfluid transfers a sudden burst of its rotational energy to the crust, giving the entire star a noticeable kick, a glitch. This means we are indirectly detecting the quantum behavior inside a star thousands of light years away. The outer core, with its eternal, perfect flow, challenges everything we know about how liquids behave, proving that deep within these stellar remnants, the ordinary rules of the universe no longer apply. Yet the neutron superfluid is not entirely pure. Scattered within this quantum sea are survivors of the star's collapse, protons and electrons that escaped the merger. And in this environment of extreme pressure, these protons do something extraordinary. They pair up. This pairing transforms them into what is known as a superconductor. On Earth, superconductors are rare, lab-created materials that, when cooled to incredibly low temperatures, can conduct electricity with perfect efficiency, with no energy lost to heat or resistance. Inside a neutron star, the entire interior provides that extreme environment naturally. Here, the protons form a vast, perfect superconductor that permeates the star. This superconducting state has a peculiar property. It actively expels magnetic fields from its interior, a phenomenon called the Meissner effect. But a neutron star's magnetic field is not expelled. It is famously, overwhelmingly powerful. This presents a fascinating puzzle. How can a perfect superconductor, which should repel magnetic fields, exist inside the very object that generates the strongest magnets in the universe? The answer lies in the structure of this quantum fluid. The protons do not form a single, solid block of superconductor. Instead, physicists theorize they likely form a complex, tangled web of microscopic superconducting currents, often described as a type of quantum spaghetti. This web is threaded through the neutron superfluid, creating a mixed state where the magnetic field is not expelled, but instead is trapped within countless tiny whirlpools or vortices in the superconducting material. It is this dynamic, frenetic dance between the frictionless neutron superfluid and the perfectly conducting proton web that is thought to generate and sustain the star's titanic magnetic field. The spinning superfluid neutrons drag these proton currents, and those currents, in their turn, amplify and organize the magnetic field into beams of concentrated energy trillions of times stronger than anything on Earth. This is the engine behind the star's most dramatic displays. Those beams, sweeping through space like a lighthouse, are what we detect as the steady pulse of a pulsar. And when the star's crust cracks in a starquake, it is this immensely powerful, constrained magnetic field that snaps and reconnects, releasing those colossal bursts of gamma rays. So the quiet, perfect flow of the superfluid and the flawless conductivity of the protons are not just curiosities. They are the fundamental power source for the neutron star's visible fury, a hidden quantum dance manifesting as cosmic fireworks. But the transition from that solid crust to the flowing neutron sea is not a clean, sharp line. It is a chaotic frontier, a place where matter is subjected to pressures so contradictory that it contorts into shapes straight out of a physicist's nightmare or perhaps a cosmic kitchen. This region is the home of nuclear pasta. As we descend from the iron crust, the pressure continues to rise, but it has not yet reached the point where all atomic structure dissolves completely. The nuclei, now incredibly neutron-rich, are still holding on, but they are being squeezed from all sides. under this immense strain, they begin to merge and deform. They are no longer distinct spheres. Instead, they are pressed together into long, cylindrical tubes. Picture a bundle of unimaginably dense rods, each one a chain of fused atomic nuclei. Physicists call this phase nuclear spaghetti. Go a little deeper where the pressure is even greater, and these tubes themselves are forced to merge side by side, flattening into continuous sheets. This is nuclear lasagna, layers of nuclear material stacked upon one another. In some models, the pressure creates inverses of these shapes, like bubbles or holes within a solid nuclear background, leading to phases whimsically named gnocchi or anti-spaghetti. This is not a playful nickname for something simple. It is a serious, computational prediction for how nuclear matter behaves when caught between the hammer of gravity and the anvil of nuclear forces. This nuclear pasta is not a soft material. Simulations suggest it may be the strongest substance in the entire universe. Its tensile strength, the stress it can withstand before breaking, could be 10 billion times greater than that of high-grade steel. A fragment of this material the size of a grain of sand could hold back the weight of 1,000 ocean liners without deforming. This bizarre landscape forms a natural barrier, a final, incredibly resilient defense for the star's solid crust against the chaotic quantum ocean beneath it. It is a testament to the universe's ability to sculpt matter into forms we can scarcely conceive, using only the fundamental forces of nature as its tools. And yet, for all its incredible strength, this pasta phase is merely the gateway to the greatest mystery of all, the very heart of the star. Yet even the formidable strength of nuclear pasta is merely a transitional zone. Beyond it lies the true unknown, the final frontier of matter itself. We are now approaching the inner core of the neutron star, a place so profoundly hidden that it represents perhaps the greatest unsolved mystery in all of astrophysics. To reach it, you would have to travel through over a kilometer of the densest, most impenetrable material in the cosmos, a barrier of pure neutronium. The pressure here does not just increase, it transcends. It may exceed even the density of an atomic nucleus, meaning there is no longer any space between particles, not even at the subatomic level. In this environment, the very rules that govern particles begin to falter. The neutrons, which have held their identity against impossible odds, may finally surrender. The pressure could become so overwhelming that the neutrons themselves are crushed, their boundaries dissolving. Each neutron is made of 3 smaller particles called quarks, held together by the strong nuclear force. At the heart of a neutron star, that force might finally be overpowered. The result would be a sea of free quarks, no longer confined within individual neutrons, flowing in what physicists call quark matter. This state of matter is purely theoretical, a prediction on a chalkboard, because we cannot create such conditions in any laboratory on Earth. But it is not the only possibility. Some equations suggest an even stranger fate, where the quarks reorganize into a crystalline solid, a quark star within a star. Others propose the formation of exotic particles like Hyperons or pions, entities that cannot exist under normal conditions. The truth is, we simply do not know. This inner core is shielded from us by that immense overburden of dense matter. We cannot see it, we cannot probe it directly. All we have are the faint signals from the star's surface, its spin and its glitches, which act like distant echoes from a hidden chamber. Deciphering what those echoes mean is the work of a generation of scientists. They use massive supercomputers to run simulations, testing each theoretical model against the scant observational data we have. The core remains a puzzle, a blank space on the map of physics that challenges our deepest understanding of what matter is and what it can become. The strangest possibility for the core begins with a simple, profound question. What happens when you squeeze a neutron so hard that it breaks into something even more exotic? One compelling answer leads us to Hyperons. Inside a normal neutron, the three constituent quarks are of two familiar types, up quarks and down quarks. But under the astronomical pressures at a neutron star's heart, the energy may be so intense that it transforms some of those down quarks into a third, far more unusual variety, the strange quark. A neutron that gains a strange quark is no longer a neutron. It becomes a hyperon, a heavier, unstable particle that cannot exist under normal conditions on Earth. In the core's extreme environment, these hyperons could form in vast numbers, mixing with the remaining neutrons and protons to create a bizarre new state of matter, Hyperon matter. This exotic soup would behave very differently than a pure neutron fluid. Hyperons interact via the strong nuclear force, but in a subtly distinct way that makes the overall material softer, more compressible. Think of it like the difference between a firm memory foam mattress and a soft down pillow. If you apply the same weight, the pillow compresses more easily. This softness is what physicists call a softer equation of state. For a neutron star, this has a critical, observable consequence. A core full of hyperon matter would be more squeezable under its own immense gravity. This means a star with a hyperon core could not support as much mass before collapsing into a black hole. Its maximum possible size would be smaller. Herein lies the Hyperon crisis. Astronomers have now observed neutron stars with masses approaching 2.1 times that of our Sun. These are incredibly hefty objects. If hyperons make the core too soft, how can these massive neutron stars even exist? Their very detection pushes theorists to refine the models. Perhaps the hyperons interact in more repulsive ways at such densities, stiffening the material against collapse. Or maybe another, even stranger form of matter intervenes. The Hyperon hypothesis beautifully illustrates the scientific tug-of-war at play, where an elegant theoretical idea meets the uncompromising data from the cosmos, forcing us to think deeper about what truly lies within. Another possibility pushes the concept of density to its absolute logical extreme. What if the pressure at the core is so phenomenally high that it does not just create new particles, but erases the old ones entirely? In this scenario, the neutrons themselves cease to be. The very idea of a proton or a neutron becomes meaningless because the pressure overpowers the strong nuclear force that binds their components together. The walls of their subatomic prisons shatter. What is left is a seething, primordial soup where the fundamental building blocks of matter, the quarks and the gluons that normally glue them together, are set free to roam. This state is known as deconfined quark matter or a quark-gluon plasma. To find a similar condition in the universe's history, you would have to rewind time to the first microseconds after the Big Bang, when the entire cosmos was a scalding, featureless sea of these free particles. Inside a neutron star's heart, this ancient state of being might be preserved, a fossil of the universe's first moments locked in perpetual stasis under billions of tons of pressure per square centimeter. This leads to a staggering theoretical possibility, the strange star. If a neutron star's core transition is complete, the entire object might not be a neutron star at all, but a star made almost entirely of this quark matter. A strange star would be even denser and more compact than its neutron cousin, a perfect self-bound droplet of pure quark fluid. Its surface would not be a solid iron crust, but a boundary a mere atom thick, separating the vacuum of space from an unbroken ocean of quarks. In this quark ocean, the particles could pair up in ways that again defy normal physics, forming a color superconductor, a superfluid state for quarks that would be even more efficient and bizarre than the neutron superfluid in the outer layers. This would add a profound new layer of quantum complexity to the core's hidden dynamics. The challenge, as with all theories about the inner sanctum, is evidence. How could we ever tell if a distant point of light is a neutron star or a strange star? the differences might be subtle, hidden in the precise relationship between a star's mass and its radius, a measurement that pushes our telescopic abilities to their very limit. The quest to find one is a hunt for a ghost, a search for an object that may be the ultimate form of condensed matter in the cosmos. But the strangeness of quark matter may not end with its mere existence. At these extremes, another layer of quantum magic emerges, one that pushes our understanding of perfection to its absolute limit. We must venture into the hypothesis of color superconductors. Recall that in the outer layers of the neutron star, protons pair up to form a superconductor, allowing electricity to flow without resistance. Now, imagine applying that same principle, but to the fundamental quarks themselves. In the unimaginable cold and density of the inner core, the free quarks would not simply float in a soup. The physics suggests they could be compelled to pair up, much like dancing partners locking into a precise, unbreakable formation. This pairing would not be based on electrical charge, however. It would be based on color charge, the property that governs the strong nuclear force. The result is a color superconductor, a state of matter where color charge, not electricity, flows without any resistance whatsoever. This is not just an improvement on earthly superconductors, it is a transformation of the concept. It would be, by definition, the most perfect superconductor in the entire universe. Physicists, with their characteristic flair, have given different possible arrangements whimsical names. One leading candidate is called the color flavor locked phase, or CFL phase, where the quark's color and flavor properties become inextricably linked in a rigid, symmetric pattern. Think of it as a cosmic ballet performed at absolute zero, where every particle's movement is perfectly choreographed with every other forever. The implications of such a state are staggering. A color superconducting core would fundamentally alter how the star manages heat and magnetism. Heat, which is just the random jostling of particles, would be suppressed in this perfectly ordered quantum fluid. Magnetic fields, which are normally expelled from a superconductor, could be frozen into a permanent, tangled lattice within the core, influencing the star's explosive behavior at the surface for millions of years. This hypothesis represents the ultimate triumph of the theory of quantum chromodynamics under the most severe pressure imaginable. It is a prediction of breathtaking elegance, suggesting that deep within these stellar corpses, the universe achieves a kind of flawless, frictionless order that we can only describe in the language of mathematics. It is the final, logical step in a journey of increasing perfection, from a solid crust to a frictionless neutron superfluid, to a core of pure, freely flowing quarks locked in perfect, eternal harmony. The ultimate test for these strange possibilities lies not in a telescope, but in a set of equations. To choose between a Hyperon core, a quark sea, or a color superconductor, physicists turn to a single, crucial concept, the equation of state. Think of it as the master blueprint for all of creation under pressure. It is a mathematical relationship, a fundamental rule that describes how any material responds when you squeeze it. For something ordinary like air or water, this relationship is simple. But for the matter inside a neutron star, the equation of state is the universe's deepest secret, a code that dictates how stiff or soft this exotic substance truly is. Every theoretical model for the core predicts a different equation of state. A core filled with hyperons, for instance, creates a softer, more compressible material. Imagine pressing down on a soft memory foam pillow. It yields easily, compacting under the weight. A star with this softer equation of state would be more squeezable under its own gravity, resulting in a smaller overall size for a given mass. In contrast, a core of pure, deconfined quark matter, especially in a color superconducting state, could be incredibly stiff, more like a perfectly rigid spring. This stiffer equation of state resists compression fiercely, allowing the star to support more mass and maintain a larger radius without collapsing. This is the crucial link between the unseen and the seen. The equation of state is the invisible bridge connecting the wild physics of the inner sanctum to the properties we can actually measure from thousands of light years away. Astronomers do not see equations, they see stars. They measure two things: a neutron star's mass and its radius. Each possible equation of state predicts a specific relationship between these two numbers. A stiffer blueprint allows for a heavier star with a larger girth. A softer blueprint limits the star to lower masses and tighter confines. So, by carefully observing the population of neutron stars, weighing them and estimating their sizes, scientists can begin to rule out entire families of equations of state. Each new massive neutron star discovered is a constraint, eliminating the blueprints that are too soft to support it. Each precise measurement of a star's diameter challenges the models that are too stiff. It is a process of cosmic deduction, using the stars themselves as forensic evidence to reverse engineer the laws governing matter at densities beyond comprehension. The equation of state is more than math. It is the key that will one day unlock the final door and tell us what truly lies at the heart of a neutron star. These abstract equations find their ultimate test in the cold, dark reaches of space. The universe itself provides the laboratories in the form of real neutron stars we can actually observe. We do not need to build a particle accelerator the size of a solar system, because nature has already built them for us, scattered across the galaxy. Our most powerful tools for this investigation are not just telescopes but clocks. This is where pulsars become indispensable. A pulsar is a rapidly spinning neutron star with a powerful magnetic field that is tilted relative to its axis of rotation. Like a lighthouse beam sweeping across a dark sea, this field channels radiation into two narrow cones. If one of those cones happens to point toward Earth once per rotation, we see a regular, repeating pulse of radio waves, or sometimes X-rays or gamma rays. The precision of this pulse is breathtaking. Some pulsars rival atomic clocks in their regularity, ticking with a stability that allows astronomers to detect deviations as small as 1 part in a billion. It is within these tiny, exquisite irregularities that the secrets are hidden. A sudden glitch in the timing, that tiny speed up, is our direct evidence for the superfluid vortexes unpinning inside the star. A gradual, exquisitely measured slowdown in the spin tells us about the star losing energy. Even more remarkably, by monitoring the pulses from an array of pulsars across the galaxy, scientists can listen for the faintest ripples in spacetime itself. As a gravitational wave from a distant collision passes between us and a pulsar, it minutely stretches and compresses the fabric of space, causing the pulse to arrive a fraction of a second early or late. This technique, called a pulsar timing array, turns these stellar corpses into a galaxy-spanning gravitational wave detector, allowing us to hear the low-frequency hum of merging supermassive black holes. Each precise tick is a message, a data point in a cosmic telegram about the star's interior and the universe around it. But pulsars are not our only window. Some neutron stars have companions. In a binary system, a neutron star can orbit another star, a white dwarf, or even another neutron star. When the pair is close enough, the neutron star's immense gravity can begin to steal gas from its partner. This stolen matter does not fall gently. It spirals in at tremendous speed, forming a superheated disk of plasma around the neutron star before finally crashing onto its surface at nearly the speed of light. This process of accretion releases a phenomenal amount of energy, primarily in the form of X-rays. Our X-ray space telescopes like Chandra or XMM Newton become our stethoscopes. By analyzing the spectrum of this X-ray light, scientists can look for the chemical fingerprints of different elements in the hot gas. They can measure the temperature of the star's surface, which tells us about how heat is conducted through its crust. They can even watch as the intense X-ray emission from the hotspots where matter is falling causes the entire star to pulse, allowing them to map its surface and measure its size. Knowing both the mass from the orbital dynamics of the binary and the radius from these X-ray observations is the holy grail. It gives us one single, critical data point to plot against the theoretical equations of state. Each binary system is a unique experiment, a chance to weigh and measure a neutron star under natural conditions we could never replicate. Through these distant cosmic laboratories, the lighthouses and the binary thieves, we gather the faint whispers of data that slowly, painstakingly, constrain the infinite possibilities of what might lie within. The precise relationship between a neutron star's mass and its radius is the most important clue we have. It functions as a cosmic fingerprint, unique to whatever exotic substance makes up its heart. Picture a sealed metal ball. You cannot see inside it, but if you could weigh it and measure its exact diameter, you could make a very educated guess about what it is made of. A ball of solid lead will be much smaller and denser than a ball of aluminum weighing the same amount. This is the essence of the mass-radius relation. For a neutron star, the stakes are infinitely higher. The measurement tells us the equation of state, that fundamental rule for how matter behaves under ultimate pressure. A star that is both very massive and very large in radius implies a stiff interior, one that fiercely resists being squeezed smaller. This points toward a core dominated by familiar, though densely packed, neutrons. But if we find a massive star with a surprisingly small radius, it tells a different story. A small, heavy star is one that has been compressed more easily. Its core must be softer, more willing to collapse in on itself. This is the signature of exotic matter like Hyperons or free quarks, which allow for greater compression under the same crushing weight. So, how do you measure the size of a city-sized object thousands of light-years away? This is the monumental task of missions like NAS, a Neutron Star Interior Composition Explorer, or NICER. Mounted on the International Space Station, NICER is not a traditional telescope. It is an X-ray timing instrument, a supremely sensitive stopwatch for the hottest light in the universe. It stares at pulsars, those spinning neutron stars that act like cosmic lighthouses. As the star rotates, hot spots on its surface, often at its magnetic poles, sweep into and out of our view. NICER measures the subtle changes in the X-ray brightness with phenomenal precision, tracing the light curve of each rotation. From the precise shape and timing of these pulses, scientists can perform a feat of astronomical tomography. They can essentially map the hotspots and, crucially, deduce how much the light is bent by the star's own immense gravity. This gravitational lensing effect depends directly on the star's compactness, the ratio of its mass to its radius. By combining this data with an independent measurement of the star's mass, often from its orbital motion in a binary system, the NICER team can solve for both numbers. It is a painstaking process of collecting millions of X-ray photons and running them through complex models, but the results are beginning to draw boundaries on the map of the possible. Each new measurement, each precise data point for a neutron star's mass and radius, acts like a verdict. It rules out entire families of theoretical equations of state, eliminating those that cannot explain the observed pairing. This ongoing detective work is slowly but surely narrowing the infinite possibilities for the core down to a set that agrees with reality. We are weighing and measuring the impossible, using the stars themselves to tell us what they are made of. This theoretical detective work, however, is no longer confined to studying solitary stars. The universe has provided us with a far more dramatic laboratory, a cosmic collision of unimaginable scale. On August 17, 2017, a ripple in spacetime washed over our planet. For 100 seconds, the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, felt the fabric of the universe itself tremble. This was not the signature of black holes, which produce a clean, rising chirp. This signal was different, longer, and accompanied by a telltale afterglow in the electromagnetic spectrum. For the first time in history, humanity had detected the collision of two neutron stars. This event, named JW170817, marked the dawn of multi-messenger astronomy, where we observe the cosmos not just with light, but with gravitational waves, particles, and more. It was a revolution. The gravitational waves told us the story of the dance. As the two stars, each about 1.4 times the mass of our Sun, spiraled closer and closer over millions of years, they stretched and distorted each other's structure through immense tidal forces. This tidal deformability, a measure of how squishy or rigid a neutron star is exquisitely sensitive to its internal makeup. A star with a soft, exotic core will deform more easily than a stiff one. By analyzing the gravitational wave signal, physicists could extract this property, providing a powerful new constraint on the elusive equation of state. It was like listening to the sound of two bells ringing as they crashed together, the tone revealing the material they were made of. Then, just 1.7 seconds after the merger, a gamma-ray burst was detected. Hours later, observatories around the world swiveled to the pinpointed location in a distant galaxy. What they saw was a kilonova, a brilliant explosion 1,000 times brighter than a typical nova. This was the aftermath. In the cataclysm of the merger, dense neutron-rich material was blasted into space. In this cosmic cauldron, rapid neutron capture processes forged elements heavier than iron. For the first time, we had direct observational proof that these spectacular collisions are the primary cosmic forges for elements like gold, platinum, and uranium. The light from the kilonova carried the spectroscopic fingerprints of these heavy metals being synthesized in real time. So, from a single event, we gained profound dual insights. We probed the fundamental nature of matter at its most extreme, using the star's final embrace to test our theories of their interiors. Simultaneously, we witnessed the origin story of the very atoms that make up our most precious jewelry and the radioactive heart of our planet. This one collision told us not only what neutron stars are, but what they do for the universe. They are both the ultimate state of matter and the alchemists of the cosmos, transforming pure neutronium into the building blocks of worlds. Even the most perfect quantum pressure has its breaking point. For a neutron star, this limit is not a suggestion. It is an absolute cosmic law. There exists a maximum mass that this exotic form of matter can support, a final line beyond which even the fierce repulsion of degenerate neutrons and the strange stiffness of quark matter must admit defeat. This ultimate boundary is known as the Tolman-Oppenheimer-Volkoff Limit, named for the physicists who first calculated it. Think of it as the universe's own weight limit for a neutron star. If the star's mass exceeds this critical value, gravity wins the final battle. The inward pull becomes so overpowering that no known force in physics can counteract it. The star's core, unable to bear the load any longer, continues its collapse uninterrupted, vanishing past the point of no return to form a black hole. The exact number for this limit, however, is not written in stone. It is written in the equation of state. A core made of softer, more compressible exotic matter will reach its breaking point at a lower mass. A stiffer core, perhaps made of pure, free quarks, can shoulder a heavier burden. Therefore, finding the true Tolman-Oppenheimer-Volkoff limit is not just about a number, it is a direct way to probe the star's hidden heart. Every massive neutron star we discover acts as a benchmark, pushing that possible limit higher and higher. Stars like Pulsar J0740+6620, a pulsar with a mass measured at around 2.1 times that of our Sun, are cosmic heavyweights. Their very existence is a powerful statement. They tell theorists that any equation of state which predicts collapse at, say, 1.8 solar masses is simply wrong. The core cannot be that soft. These massive survivors ruthlessly eliminate entire families of theoretical models, particularly those that rely heavily on hyperons or other forms of matter that compress too easily. They force the equations to be stiffer, pointing toward interiors that are incredibly resilient, perhaps dominated by free quarks in a color-superconducting state. So, the hunt for the most massive neutron star is a hunt for the truth. Each new record holder helps us draw a line in the sand of physics, narrowing down the possibilities for what matter can become when it is pressed to the absolute edge of existence. The ultimate fate of a neutron star is written not in its spin, but in its fading warmth. Born in the cataclysm of a supernova, these stellar remnants enter the universe at temperatures exceeding 1 billion degrees, hotter than the core of our Sun. But they are not sustained by nuclear fusion. A neutron star is a cosmic ember, radiating away its primordial heat into the void over millions of years. This gradual cooling, its thermal evolution, is a silent story playing out across the galaxy, and the speed at which it cools holds direct clues to the deepest secrets of its interior. For astronomers, this is a patient science. They search for neutron stars of known ages, often by associating them with the supernova remnants from their violent births. Using powerful X-ray telescopes, they then measure the temperature of the star's surface, that thin iron crust. It is a monumental technical challenge, like trying to measure the warmth of a single candle on the moon. But when successful, it provides a critical data point, a snapshot of the star's internal temperature at a specific moment in its multi-million-year life. Plotting these snapshots for stars of different ages creates a cooling curve, a thermal fingerprint of the neutron star's life story. The shape of this curve is dictated entirely by the physics happening deep within. For a long time, the dominant cooling theory was straightforward. A young neutron star cools rapidly by emitting a flood of neutrinos, those ghostly particles that barely interact with matter directly from its hot core. After 1 million years or so, this neutrino emission slows, and the star switches to a slower cooling phase, radiating primarily photons from its surface. This standard model produces a predictable cooling timeline, but the universe, as always, enjoys surprises. Observations have revealed neutron stars that are significantly colder than this standard model predicts. They have lost their heat far too quickly. This is where exotic matter enters the story. If the core contains hyperons or free quarks, it opens up powerful new avenues for neutrino production. These exotic particles can interact and decay in ways that generate neutrinos with extraordinary efficiency. It is like discovering a hidden drain in a bathtub, a new channel that allows the star's thermal energy to escape into space at a vastly accelerated rate. A neutron star with a hyperon or quark matter core would cool like a stone in a winter river, its internal heat vanishing on a cosmic timescale. So, when astronomers find a middle-aged neutron star that is mysteriously cold, it raises a compelling possibility. They may be looking at the thermal signature of an exotic core, a direct observational hint that the star's heart is made of something beyond ordinary neutrons. This slow, patient study of stellar cooling is a complementary test to the violent snapshots from mergers or the precise measurements of mass and radius. It does not give an instant answer, but over decades, as more stars are measured and added to the chart, the collective thermal history of these cosmic corpses will either confirm or constrain our wildest theories about the strangest matter in the universe. But a neutron star's magnetic fury has an even more extreme expression. Among these cosmic powerhouses, there exists a special class that redefines the very meaning of magnetic field. They are called Magnetars, and they are the universe's true magnetic monsters. While a typical pulsar's field is already trillions of times stronger than Earth's, a magnetar's field is another 1,000 times stronger than that. To grasp that scale, imagine a magnet so powerful that if it were placed halfway between the Earth and the Moon, it could strip the data from every credit card on our planet. This is not a gentle force, it is a titanic, distorting pressure that grips the entire star. The origin of this unimaginable strength lies in the chaotic dance of the interior we have already explored. Recall the superfluid neutron ocean and the superconducting proton web. In a magnetar, this internal dynamo is thought to have been wound up to an extreme during the star's violent birth. Perhaps the progenitor star was spinning exceptionally fast, or the collapse was unusually asymmetric, twisting the magnetic fields like a coiled spring as the core condensed. This process, known as the dynamo effect, amplifies the field to these staggering levels. The magnetic field is not a passive feature, it is an active, living force that shapes the star's very structure. It exerts such immense stress on the solid iron crust that it can literally bend and warp it. The crust, for all its incredible strength, is not infinitely rigid. Under this constant, twisting pressure, it builds up strain like tectonic plates on Earth grinding against one another. Eventually, the stress becomes too great. The crust fractures. This is a starquake, but on a scale that makes terrestrial earthquakes seem like whispers. When a magnetar's crust cracks, it releases more energy in 1/10 of a second than our Sun will emit in 100,000 years. The entire star vibrates, ringing like a bell struck by a god. This sudden shift in the crust has a direct, terrifying link to the magnetic field anchored within it. The field lines, which are frozen into the superconducting interior and threaded through the crust, are violently snapped and rearranged. This magnetic reconnection converts the pent-up energy of the field into a torrent of radiation. The result is a colossal flare of X-rays and gamma rays, a burst of light so intense it can temporarily outshine every other source in our galaxy, even from tens of thousands of light years away. In 2004, a magnetar flare from a star in the constellation Sagittarius was so powerful that it actually ionized Earth's upper atmosphere from 50,000 light years away, affecting long-range radio communications. These events are the most dramatic demonstrations that the bizarre quantum physics inside a neutron star is not an abstract curiosity, it is a raw cosmic power source. The frictionless superfluid, the perfect superconductor, and the unbreakable nuclear posture all work in concert to create and sustain a magnetic prison of unimaginable force. And when that prison breaks, even for an instant, the universe feels the shock. The surface of a magnetar may crack, but the entire star can ring. This phenomenon offers a startling new way to listen to the hidden depths of these cosmic objects, a field known as neutron star seismology. Just as geologists decipher the Earth's layered interior by studying the seismic waves from earthquakes, astrophysicists believe the oscillations triggered by a starquake can carry encoded information about everything from the crust's rigidity to the superfluid's behavior deep within. When the crust fractures, it sets the entire star vibrating in distinct patterns, like striking a bell to hear its unique tone. These are not random shudders. They are precise vibrational modes, each telling a different part of the story. Some oscillations are pressure waves, compressing and expanding matter as they travel through the star's body. Others are gravity waves, rippling at the boundary between different layers, like waves on the ocean's surface. Crucially, different modes penetrate to different depths. A high-frequency vibration might only probe the outer crust, while a deeper, lower-frequency oscillation could travel all the way down to the interface of the outer core and the enigmatic inner sanctum. By theoretically modeling these vibrations, scientists create a library of possible stellar songs. Each model, based on a different assumption about the interior composition, predicts a unique set of frequencies. The dream is to then match these predictions to an actual detection. How could we possibly hear a star ringing across the void? the clues might appear in the incredibly regular pulse of a pulsar. A global oscillation would minutely distort the star's shape, causing a temporary, rhythmic wiggle in the timing of its lighthouse beam. Alternatively, in the brilliant X-ray flare following a magnetar starquake, the fading light itself might carry an imprint of these vibrations, flickering with a hidden seismic code. This nascent field, sometimes called astroseismology, promises a more direct sonic probe. It would not just weigh or measure the star from the outside, but listen to its internal echoes. A successful detection would allow us to seismically map the density and stiffness of each layer, from the crystalline mountains of the crust, through the bizarre nuclear posture, and right to the very edge of the mysterious core itself. It would be like developing a cosmic stethoscope, turning the most violent events in the universe into a tool for profound discovery. The boundary between a neutron star and a black hole is not a clean line, but a cosmic cliff. Physics tells us there is a limit to how much mass a neutron star can support before it collapses forever. But nature, in its infinite complexity, may have left a final puzzle in the space between these two destinies. Astronomers call it the mass gap. On one side, we have the most massive neutron stars ever observed, approaching 2.2 times the mass of our Sun. On the other side, we have the lightest known black holes, starting at around 5 solar masses. Between 2.2 and 5 solar masses, there is a mysterious desert where very few compact objects have been found. This gap is not necessarily empty, but it represents a zone of profound instability. It is the ultimate testing ground for the equation of state. If neutron star matter is incredibly stiff, the maximum mass could be high, shrinking this gap. If it is soft, the gap widens. But what if the objects that form here are neither classic neutron stars nor classic black holes? This is where theory ventures into truly exotic territory. An object born in this precarious zone might initially look like a neutron star, but its core pressure could be so immense that it immediately triggers a phase transition to quark matter. The entire star might become a strange quark star, a self-bound droplet of pure quark fluid that is stable at a higher mass than a neutron star could ever be. Or perhaps it forms as a hybrid star with a normal neutron star mantle surrounding a massive, permanent core of free quarks. These theoretical objects could potentially inhabit the mass gap, acting as a missing link in the family tree of stellar corpses. Finding one would be a monumental discovery. It would be direct evidence that quark matter is not just a speculative possibility in the deepest cores, but a stable, dominant phase of matter that can define an entire celestial body. The hunt for these gap objects is now a major focus of astronomy. When LIGO detects the ripples from a collision, the masses of the objects involved are measured with stunning precision. A few events have already hinted at compact objects falling within this ambiguous range, sparking intense debate. Are they very heavy neutron stars, very light black holes, or something entirely new? Each candidate is a clue. The mass gap, therefore, is more than just an empty stretch on a chart. It is a frontier. Its very existence, and what we eventually find within it, will force a fundamental rewrite of our understanding. It asks the ultimate question about the end of a star's life. When matter is pushed beyond every limit we know, what is the final, true form it can take before it vanishes from the universe entirely? The violent collisions of neutron stars in deep space have a tiny, fleeting counterpart here on Earth. In laboratories like the Relativistic Heavy Ion Collider in the United States and the Large Hadron Collider in Europe, scientists perform their own microscopic versions of a cosmic cataclysm. They do not use stars, of course, but subatomic particles. Inside these circular tunnels, stretching for miles, they accelerate heavy atomic nuclei to over 99.99% the speed of light, and then smash them together head-on. For a fraction of a second, in a space smaller than a single atom, the collision creates a fireball of unimaginable heat, reaching trillions of degrees. In this inferno, protons and neutrons melt away, and for a fleeting moment, their constituent quarks and gluons are set free. This is the quark-gluon plasma, the same primordial state of matter that existed microseconds after the Big Bang, and that may exist at the heart of a neutron star. But there is a crucial difference. The quark-gluon plasma created in our colliders is incredibly hot and relatively thin, like a sparse, blazing fire. Inside a neutron star, the quark matter would be unimaginably dense and comparatively cold, more like a frozen, hyper-compressed ocean. These two states are like opposite corners on a vast and largely unknown map, a chart physicists call the phase diagram of nuclear matter. This diagram is a fundamental blueprint of reality, showing how the strong nuclear force organizes quarks and gluons under every conceivable condition of temperature and density. Our particle accelerators explore the high-temperature, low-density region. Our telescopes and gravitational-wave detectors probe the low-temperature, high-density realm of neutron stars. Neither method can see the whole picture alone, but by combining the data from these wildly different experiments, one in a controlled lab and the other in the wild cosmos, we begin to connect the dots. Each new measurement from a collider, telling us how this exotic soup flows and interacts, informs the theoretical models for what happens under the crushing weight of a stellar corpse. And every new observation of a neutron star's mass, radius, or cooling rate tests those same models from the other direction. This is the grand synthesis of modern physics, where the smallest experiments and the largest cosmic events are woven together into a single quest to understand the ultimate rules that govern matter itself. The mathematics governing the heart of a neutron star is the most formidable puzzle in physics. The fundamental theory we have for this realm is quantum chromodynamics, or QCD. It is the rulebook for the strong nuclear force, the glue that holds quarks together inside protons and neutrons. In principle, QCD should tell us everything about a core of pure quark matter. In practice, it presents a wall of pure complexity. The challenge lies in the unique conditions. A neutron star's core is a place of incredible density but relatively low temperature. This combination falls into a regime physicists call non-perturbative. In simpler terms, the interactions between quarks and gluons here are so intense and so constant that our usual mathematical shortcuts, the ones that work beautifully in particle colliders, completely break down. The equations become a tangled web with no clear starting point for a solution. It is like trying to predict the exact pattern of a raging storm by only understanding how a single drop of water falls. The sheer number of interactions is overwhelming. This is why we cannot simply plug the numbers into a computer and get an answer. The core's equation of state remains hidden behind a curtain of calculation so difficult it demands the most powerful supercomputers on Earth, running for years. To even attempt a glimpse, theorists use a brilliant workaround called lattice QCD. Imagine the continuous space and time inside the core being overlaid with a fine, four-dimensional grid, like a fantastically complex chessboard in 4 dimensions. By placing the quarks and gluons on the points and links of this lattice, physicists can simulate their interactions numerically, but there is a catch. Lattice QCD works best at high temperatures or at lower densities, the conditions we can create in colliders. To reach the crushing densities of a neutron star core, the calculations require immense computational power and clever mathematical tricks to extrapolate into the unknown. Each simulation is a monumental effort, a digital expedition into a territory where the map is being drawn as we walk. These theoretical tools are our only bridge from the clean, elegant rules of particle physics to the messy, overwhelming reality of a stellar interior. They transform the grand mystery of the core into a series of precise, if agonizingly difficult numerical problems. Every advance in computing power, every new algorithmic breakthrough, brings us a step closer to solving the ultimate equation written in the heart of a star. The neutron star is more than a cosmic object. It is a philosophical question made of matter. To stand before its reality is to confront the very definitions we use to make sense of the universe. What does it mean for something to be solid when its strength comes from quantum degeneracy pressure, not chemical bonds? What is a fluid when it flows without friction for all eternity? Inside that star, our comfortable categories of solid, liquid, and gas dissolve into irrelevance, replaced by phases with names like nuclear poster and color superconductors. Here, identity itself becomes fluid. In the superfluid core, can we truly speak of individual neutrons, or are they all part of one collective quantum wave, a single entity acting in perfect unison? Where does one particle end and another begin when they are all described by the same probability function? This challenges a very human way of seeing the world, where objects have distinct boundaries and properties. The neutron star forces us to accept that at its most fundamental level, reality is not a collection of tiny billiard balls, but a tapestry of interconnected fields and probabilities. It is a natural laboratory operating at the absolute edge of physical law, a place where the universe itself is conducting experiments in states of being we can only theorize. Understanding it, then, is not merely an exercise in astrophysics. It is an attempt to map the outermost borders of what is possible. Every equation of state we test, every glitch we analyze, is a step toward answering a deeper question. What forms can matter take before the rules themselves break down and surrender to a black hole's silence? This stellar remnant is a beacon at the frontier of knowledge, illuminating not just the darkness of space, but the limits of our own understanding. The ultimate answers will not come from our current tools, but from the next generation of eyes and ears we are now building for the cosmos. Our understanding of neutron stars stands on the brink of a revolution, driven by observatories so advanced they will turn today's best guesses into tomorrow's confirmed facts. Leading this charge is the European Space Agency's Athena mission, an X-ray observatory of unprecedented power. While current telescopes can glimpse the hot surfaces of these stars, Athena will study them with a clarity we have never before possessed. It will measure the faint X-ray emissions from neutron stars with such precision that scientists can map temperature variations across their surfaces in fine detail, almost like taking their thermal portrait. This will allow us to see how heat is conducted through that iron crust and radiated away, providing a direct test of the exotic cooling models. More importantly, Athena will refine our measurements of neutron star radii to a degree of accuracy that is currently impossible. By observing how X-rays from a pulsar's hotspots are lensed and distorted by the star's own gravity, Athena will pin down the mass-radius relation for multiple stars, delivering the crisp, clean data points needed to finally rule out whole families of competing equations of state. On the ground, a new era of listening has already begun. The next generation of gravitational-wave detectors, projects like the Einstein Telescope in Europe and Cosmic Explorer in the United States, are designed to be 10 times more sensitive than our current instruments. They will not just hear the rare, loud crashes of neutron star mergers, they will tune into a constant, rich chorus of them from across the universe. With this vastly expanded catalog of collisions, each gravitational wave signal will act as a precise probe of the star's internal structure. The way the stars stretch and deform each other in their final moments, their tidal deformability, is encoded in the shape of the wave. By detecting hundreds of these events, scientists will statistically determine the true stiffness of neutron star matter. It will be like moving from examining a single, unique bell to listening to an entire orchestra of them, each ringing with the distinct tone of its internal composition. This flood of data will provide the most stringent constraints yet on what can and cannot be happening inside that hidden core. Simultaneously, the radio sky will be surveyed with new depth by immense telescope arrays. Projects like the Square Kilometre Array will scan the heavens with such sensitivity that they are expected to discover tens of thousands of new pulsars, effectively mapping the galaxy's population of these cosmic lighthouses. Among this vast haul, they will find rare and precious systems like pulsars orbiting other dense objects with exquisite timing. These binary systems are natural laboratories for testing gravity and measuring mass. By tracking the subtle wobbles in a pulsar's clockwork pulse as it orbits a companion, astronomers can weigh both objects with astonishing accuracy, often too within a fraction of a percent. Finding more of these precise cosmic scales, especially around the theoretical upper mass limit, will directly challenge our models. Is there a sharp cutoff at 2.2 solar masses, or do we find stars even heavier, pushing the Tolman-Oppenheimer-Volkoff limit higher and demanding an ever stiffer core? Together, these missions form a coordinated assault on the mystery. Athena will give us exquisitely detailed portraits. The new gravitational-wave observatories will let us feel the star's squishiness in a cosmic collision, and the radio arrays will conduct a vast census weighing thousands of stellar corpses. Each tool probes a different facet of the same profound question. Within the next few decades, the convergence of their data will create an undeniable picture. The theoretical possibilities that now seem equally plausible will be winnowed down by hard evidence. The strange hypotheses of quark matter, color superconductors, and Hyperon cores will no longer be just elegant lines in a theoretical paper. They will either be confirmed as the fabric of reality or gently placed back on the shelf, replaced by a truth even more astonishing. We are building the instruments that will finally open the sealed chamber at the heart of a neutron star, allowing us to read the universe's own blueprint for matter at its absolute limit. The true portrait of a neutron star is not painted by a single observation, but by a symphony of them. We have journeyed through its theoretical layers, from the crystalline mountains of its crust to the possible sea of free quarks at its heart. Each layer, from the nuclear poster to the color superconductor, is not an isolated idea. They are all expressions of a single, underlying truth, the equation of state. This fundamental rule is the master key, and every astronomical tool we have is designed to turn it. The precise pulse of a lighthouse pulsar gives us a mass. The bent X-ray light from its hotspots hints at a radius. The unexpected coldness of a middle-aged star whispers about rapid neutrino cooling. The gravitational wave chirp from a cataclysmic merger tells us how much the stars deformed before they collided. Alone, any one of these clues is intriguing but inconclusive. A cold star could have several explanations. A specific mass-radius pair could fit multiple theoretical curves. But together, these multi-messenger observations weave a constraining web. They eliminate possibilities. They rule out entire families of equations of state that cannot explain all the data simultaneously. It is a process of cosmic triangulation using sight, sound, and touch to map a hidden continent. The current scientific consensus reflects this careful synthesis. The outer layers, the iron crust, and the neutron superfluid ocean are now on solid theoretical ground, strongly supported by the observed behavior of pulsar glitches and starquakes. It is the inner core, that final sanctum, that remains the active and thrilling frontier. Here, the data is still too sparse, the constraints too loose. The theories of Hyperon matter, Quark-Gluon plasmas, and color superconductors all still live within the bounds of what we have observed so far. This is not a failure of science, but its very essence. The puzzle is immensely complex, a 1,000-piece jigsaw where we are still sorting the edge pieces from the middle. Yet with every new astronomical discovery, with every massive pulsar weighed, every merger heard, and every cold star measured, another piece clicks into place. The image is coming into focus, revealing not just the anatomy of a stellar corpse, but the ultimate capabilities of matter itself. Our journey through a neutron star is a map of the impossible. We have scaled crystalline mountains of iron stronger than steel, sailed seas of frictionless neutrons that spin forever, and peered into a theoretical heart that might be made of free quarks or perfect color superconductors. This is not science fiction, but the revealed architecture of our cosmos under pressure. These stellar remnants are far more than celestial oddities. They are the universe's ultimate physics laboratories, operating at energies and densities we can never replicate on Earth. Every glitch in a pulsar's spin, every flash from a magnetar, is a data point in a grand experiment on quantum behavior and nuclear forces. They are also the alchemists of the galaxy, forging the heaviest elements like gold and platinum in their violent collisions, and scattering those atoms across space to one day become part of new worlds and perhaps even life. And now they are our beacons in the dark, their mergers sending ripples through space-time that we have learned to feel, opening an entirely new sense with which to perceive the universe. In their extreme existence, they teach a profound lesson about interconnectedness. The same quantum rules that govern a superfluid here in theory sculpt a star's explosive fury 100,000 light-years away. The quest to understand them pulls together the threads of particle physics, astrophysics, and gravity into a single, magnificent tapestry. This story is unfinished. The final chapter on what lies in that deepest core is not yet written. It is being composed right now in the hum of supercomputers running lattice QCD simulations, in the precise tick of a pulsar timing array, and in the silent anticipation of data from the next great observatory. The answer is still out there, spinning in the heart of a distant star, a mystery written in the language of quarks and gravity, waiting for our curiosity to decode it. If your mind is still reeling from the thought of quantum superfluids and nuclear pasta, you are in excellent company. That sense of wonder is the very engine of discovery. We would love to hear what part of this journey struck you most. Was it the idea of a single sugar cube weighing 1 billion tons, or the perfect, eternal spin of a frictionless superfluid? Drop your biggest question or most mind-blowing takeaway in the comments below. Let's continue the conversation and explore the strangeness together. To make sure you never miss our next voyage to the edges of understanding, from the event horizons of black holes to the enigma of dark matter, be sure to subscribe and tap the notification bell. You can also dive deeper right now by exploring our playlist dedicated to unraveling the universe's greatest mysteries, each video crafted to stretch your imagination. Thank you for joining this expedition into the extremes of reality. The cosmos is waiting with endless puzzles, and the next discovery is just a click away.